Okay, 9.2, we're going to take a look at something called series. And a series and a sequence are related, but they are different. So sequences are where we find sort of a list of a pattern of objects. In this case, we're looking at numbers, right? That's a sequence. What a series does is a series adds those sequence values together, okay? And it may not seem like that's a big deal, but it actually creates a really big, not necessarily a problem, but a much more difficult process than looking at sequences. So we'll start with the definition of a series. So if A sub n is an infinite sequence, then the summation from n equal 1 to infinity of A sub n, which would be A1 plus A2 plus ... plus AN plus ... because this is infinite, is an infinite series. Or we will actually just say series, because we're going to be working only with infinite series, so we're going to shorthand this to just saying series. The numbers, A1, A2, and so forth, are called the terms of the series. And what the bulk of Chapter 9 is going to be doing is looking at series and trying to decide if they converge. That's what we're going to be doing. And that may not seem like that difficult of a question, but you're going to see some nuances in it that are going to make it much more difficult. And I liken this back to Chapter 8, which is exactly what my Calc II students are doing right now as well. Calc 2 in Chapter 8, if you'll remember, is going backwards on the chain rule, right? Not the chain rule, the product rule. And it doesn't seem like it should be that difficult, but you find out very quickly it's actually really difficult. And there's a whole lot of different methods, and they don't equally work for every in situation, right? Every situation poses its own difference or own nuance. Same thing's going to happen here. So if we have this series, down here, the second definition, summation from n equal 1 to infinity of A sub n, the nth partial sum is the sum that we would get if we only do n of the terms. Okay? So it would be a finite sequence that we'd be looking at in that case. We call it an nth partial sum. If the sequence of partial sums S sub n converges to S, then the series, the summation from n equal 1 to infinity of A sub n, converges. The limit S is called the sum of the series. S is equal to A1 plus A2 all the way to AN, which is the same as the summation from n equal 1 to infinity of A sub n. And if the sequence of partial sums diverges, then the series will also diverge. Okay? So it's kind of like this. We're taking all of these sequence values, and the first S1 would just be A1, right? S2 would be A1 plus A2. And S3 would be A1 plus A2 plus A3. And S4 would be A1 plus A2 plus A3 plus A4. Okay, so the S's actually just take each of these sequences and it truncates, it stops it somewhere, and it adds up those values. Now, when you do that, you create another sequence, right? We've got a whole bunch of values. One of them stopped at 1, and one of them stopped at 2 terms, one of them stopped at 3 terms, one of them stopped at 100 terms, one of them stopped at 101 terms. And if we take a look at that sequence, and we decide if that sequence converges or diverges, then that answers the question about whether the series converges or diverges. Okay, now some of these are really easy to see. Yes, they work. No, they don't. And some of them look like they should, and they don't too. And so there's these nuances that happen, and we have to be really careful when we're looking at them, that we're thinking about the fact, are we working with a sequence or are we working with a series? Because they don't function the same way. So let's take a look at our first sort of point, or the point of all of it, and I've already mentioned it. We will spend the majority of our time in this chapter answering the following questions. Does it converge or diverge? The series. And then secondly, if it does converge, can we find its sum? And again, sometimes the answer is yes, and sometimes the answer is no. We can actually know that something converges and still not know what it converges to, which is really crazy. Because if you think about it, when we did sequences, we didn't even approach it from that perspective. We didn't even answer the question if it converged or diverged until we figured out what it converged to. Remember that? The directions always looked sort of backwards of what we actually did. They said, does it converge? If so, find its limit. And what we tried to do is we tried to find its limit, and if we were successful, then we said it converged. We won't generally be able to do that with series. We generally will have to say, yes, it converges, and then decide if we can figure out what it converges to. So these questions are much more difficult than they were for sequences. The second is especially hard and not always possible to find. Okay, so this is what we've been saying in written form. So we're going to look at our first sequence, and it's a sequence you have seen, not sequence, excuse me, series. And it is a series you've probably seen before, but we're going to look at it in a different way, of course. And this is called a geometric series. So if you take the sequence a times r to the n, and you let the n value go from 0 to infinity, this creates a plus ar plus ar squared, ar cubed, and so forth, and you're adding them all together. This is a geometric series with ratio r, and the r does not equal 0. Now, you've probably at least seen this with sequences at a couple of different places. My elementary math students have seen this with sequences very recently. And so they see something that like multiplies by 2, and so you get the next term by multiplying by 2 or by multiplying by 1/2 or something like that. So you're just multiplying by some term over and over and over again. Well, we're doing the same thing here. It's just that we're going to add them up when we do that. We're not going to actually stop with the sequence. We're going to look at the series. And this is one that's very helpful because it actually tells you if we have a geometric series with a ratio r that it will diverge when the ratio r is greater than or equal to 1. In other words, if the number we keep multiplying by every single time is bigger than or equal to 1, the thing's going to diverge. And we can see this happen really quickly with like a graph too. We'll look at it, okay? But if the ratio is between 0 and 1, and we are looking at absolute values, so I don't care what the sign is, they could be negative and that'd be okay. But if the ratio is between 0 and 1, right? So if I'm multiplying by 1/2 every time, if I'm multiplying by 1/3 every time, if I'm multiplying by 0.9 every time, it will converge. And not only will it converge, but we know what its sum will be. Its sum will be a over 1 minus r. Now notice, this form right here, a over 1 minus r, is not a form that works if it diverges, because if it diverges, this doesn't even make any sense to talk about. So you can't find a over 1 minus r and say, since I found a over 1 minus r, therefore it converges. It doesn't work like that. It converges based on what the value of r is. Okay? We definitely need an example so you can see how it works, because this one's a very friendly sequence, okay? Or series, excuse me. So here's an example. This one says, find the sum of the convergent series. It is convergent. Can you tell by the form how we could know that, even if they didn't tell us?
It says it right.
Besides the telling us part, yes. Okay, that's all right. So take a look back over here.
Fraction to a power.
Yes, there you go. Okay, so it tells us that if we have a ratio here that's being raised to a power, and that R ratio is between 0 and 1, absolute value purposely, right? It doesn't matter if it's negative. If it's between 0 and 1, it's going to converge. This one is between 0 and 1. This right here is my R. Okay? So this will converge, even if they didn't tell me it. If they asked me instead of told me, this will converge. So we're going to make the note to ourselves, not because it asked us, but because you're going to look at it later and you're going to be like, how did we know that again? Okay, so this converges because the ratio is negative 1/3, and 0 is less than the absolute value of negative 1/3 is less than 1. Okay, that's why it converges. Because it converges, we're able to do what the rest of the directions said. Find the sum. Okay, so how do we find the sum? Well, we have a formula for it. The formula for it said what? What does it say above? A over 1 minus r. Well, we've already established what the r is. R is negative 1/3. And we do have r here. It's not the absolute value of r in the formula. It is r. So it is a negative 1/3. What's a? It's 1/2. A is the value it starts at. Whoops. There we go. This right here is A. Okay. Now it does matter, and I haven't made mention of it, it does matter that this actually is a sequence, the inside's a sequence, the outer part's a series, that starts at n equal to 0. So we're going to see what happens when things don't start at 0 in a minute, but this one does start at 0. So there's no sort of, well, what about when it doesn't start at 0 yet? Okay, it starts at 0. We can fit it right back into that form. We can see very clearly there's A. A is equal to 1/2. And then we've got to simplify what we have here. So I have 1/2. This is going to be addition. So what's 1 plus 1/3? 4/3, which is 1/2 times 3/4, right? What does that give me? 3/8. So this series will converge, and it will converge to 3/8.
That's the sum.
Yes, that is the sum of our series. Exactly. That is the sum of our series.
That equals S or S sub n.
It equals S. And the reason it equals S, Ben, is because we are doing it for the infinite version, not just for a finite number of terms. This is infinite. And the reality is that's what we're going to be looking for the whole time, is we're always going to be looking for the infinite version. Okay? All right, so what would I actually have to change in order for this series to diverge? The R value. And what would it need to be, Sophia? Yeah, R would need to be greater than 1. And our R in this one was the negative 1/3, right? The negative 1/3 would need to be a number bigger than 1 or less than what? Yeah, less than negative 1. So bigger than 1 or less than negative 1. So if we had that happening, then we would not have a convergent series. Okay. So geometric series are usually really easy to sort of pick out because their form is very distinguishable, right? It always has, I'll come back over here, it always has this form right here. Whoa, that's not what I meant to do. I want to do this one. It always has this form right here. It's always some number times some other number to a power. And whatever those numbers are does not decide if it's geometric or not. They'll decide if it converges. But it's going to be geometric if we have two numbers multiplied and one of them is raised to the power n or k or whatever your index is at the bottom. Okay. Now, the next one's a little bit harder to see when it happens. This one's called a telescoping or a collapsing series. This is a type of series where the partial sums are used and the terms cancel out. So then this one's going to have those s sub n's in it, and we're going to see what happens when they cancel out. So first of all, looking at it, can you tell it's not a geometric series? Yeah, right? It doesn't look anything like it. I don't have any powers. There's not multiplication of numbers. I have multiplication of product, right? There's a product in the denominator. But it's not numbers that are being multiplied. They're variable components. This doesn't look anything like a geometric series. So you're sort of in your mind starting to tabulate all the options we have when we're considering these. We have an option of a geometric series, and now we're about to see a new one. But this one's not geometric, and it's clear that it's not, right? Okay. What I want for us to do is to write out some of the partial values. So actually, do we want to do it that way? Let's go with my notes. Let's go with my notes for the moment. I was going to go a different direction, but I'm hesitant to do that. We're going to look at something that's back in chapter 8 that you all loved. Do you remember those? Partial fractions. Do you remember them? It's an 8.3. No, it's not true. It's an 8.5. I'm going to be teaching it next Tuesday, so if you want a refresher, you can come visit my Calc II class next Tuesday. The way partial fractions work, Peter says no. Oh, you want to do? Yeah. You can come.
What time
it's Tuesday at 12:30. Yeah, you probably have classes, so you can be there. You're welcome to. Tuesday at 12:30. Partial fractions is one of the two things we're going to be looking at. Okay, so partial fractions looks like this. When you have a denominator that's in pieces, which this one is, or if it can be factored so that you can see the pieces, you should be able to somehow separate it into two separate fractions with two different, potentially different denominators. Okay, so what we're going to do is we're going to change this piece right here. I'm going to do this down here underneath this into, something over k and something over k plus 1. You're like, oh, yeah, that's ringing a bell. Okay, so the way that this works is we need to figure out what numerators need to be here, what they need to be, in order for us to merge it back together and for it to be the original 1 over k times k plus 1. And we do it like this. We let each of them have an arbitrary a and b numerator. If the denominator had been squared, right? If it said x squared plus 1 down here, or in this case k squared plus 1, then this would actually have to be linear. It would have to say bx plus c or bk plus c, right? So when we have a linear denominator, we need a constant coefficient. And then we're going to actually like merge them back together. We're going to make them back into a single fraction. It feels like we're undoing them, but it's helpful. So this one ends up being a times k plus 1, if I want the denominators to match, over k times k plus 1. And this one ends up being b times k over k times k plus 1. Except for the k's, this looks exactly like what we do in Calc 2. There's x's when we did it there. We did it for the purposes of integration. Now we're doing it for the purposes of summation. And then we merge these back together and we say, okie dokie, well, this is ak plus a plus bk over k times k plus 1. Okay, are we good so far? Yeah? I haven't answered the question yet, but I need this piece right here then to figure out what a and b have to be in order for this to give me a 1. And so I do it something like this. I say, okay, looky here. This right here is a constant. I have constants, and my constant is 1. And the constants down here are just a. A is my only constant down here. Everything else is multiplied by k. So this is the a that's down here. The other component is the linear term. So use a 1 point just a sec. The linear term, there's no linear term on top. There are no k's. So there are 0 linear terms. There's not a variable on top, in other words. There's a 0 in terms like 0 times a variable. But the two pieces that have variables in them down here are a and b. Okay? Well, the nice thing is that this is actually already solved for one of them. A is 1. I mean, like it tells us that, right? The a value is 1. So if a is 1, I should be able to solve this equation and figure out what b is. So if a is 1, what will b be? Yeah, b will be negative 1. So what that means is that this separation into two fractions now have individual numerators. The a numerator is 1 and the b numerator is negative 1. Okay? So I can now take what I was trying to do right here when I was separating, and I can finish the separation. This is 1 over k plus, or we can even say minus if you want here, 1 over k plus 1. So either do plus a negative numerator, put negative in front, doesn't matter. Okay, everybody good? Okay, now we're going to go back to what Ben had asked about on the previous problem, and we're going to look at the partial sums. So in essence, we're going to just write out a few of these terms and see what happens. So if I put in k equals 1, and then I'm going to do 2, and then I'm going to do 3, and we're just going to go down the list until you can see a pattern of what's happening here. What happens when I put in 1? Well, I'm going to have 1 over 1 minus 1 over 2, right? Okay, cool. And then I'm going to have this added to the thing that comes next. Well, now I need to put the number 2 in. So if I put the number 2 in, I'm going to have 1 over 2 minus what? 1 over 3. Now we're going to put the number 3 in. So I'm going to have 1 over 3 minus 1 over 4. Let's do one more set and I'm going to stop. What would the next set of parentheses look like? 1/4 minus 1/5. And this will keep going indefinitely until I end up having 1 over, generally n, minus 1 over n plus 1, right? And then again, it keeps going. It's infinite. It's infinite. But do you see something happening? That's part of it. We need to do that in a second, though. These pieces match. And they cancel. I have a negative 1/2 and a positive 1/2, a negative 1/3 and a positive 1/3, a negative 1/4 and a positive 1/4. And they all pair up until I get to the last term, but the problem is there is no last term, right? This piece right here is doing exactly what Dylan said. If we take the limit of this as n goes to infinity, what is the limit of 1 over n plus 1 as n goes to infinity? That's 0. So at the beginning, I have a 1, and at the end, I have 0, because that's the limit at the ending of this. This whole thing collapses. It's also called telescopes, okay? It telescopes because we're adding something in and collapsing it off, and adding it in and taking it off, and adding it in and taking it off. And this one happens to do it very nicely. It's in subsequent terms, right? It's one half here, 1/2 here, 1/3 here, 1/3 here. They could be doing it more sporadically than that. That's happening because our partial fractions gave us 1 over k and 1 over k plus 1. But imagine if this said 1 over k and 1 over k plus 2. The same thing would happen, but the collapsing pieces would be further apart from each other when we write out the limit, or I'll write out all these pieces of it, right? All these terms. So it could still collapse, even if it doesn't collapse right beside each other. It's still possible for it to collapse. At the end of all this, I said it, but I didn't write it, we get 1 minus 0, or just 1. That's the sum of this convergent series. Are they all going to be 1? No, they're not all going to be 1. Depends on the pieces that we're starting with. Well, actually, all these pieces that we were finding, so like this one right here is S1, and then this right here is S2, and this right here, we'll do green, would be S3, and so on. Yeah. So we ended up finding an expression for combining them all together. So what we actually ended up having, if I hadn't put the dot, dot, dot here on the end, would have been S sub n. Yeah. Okay, ready for another one? So this is the kind of example that I would do in one of my elementary math classes, but they're not going to see it the way you're going to see it at all. They do it from a very, very different perspective. This wants you to write a repeating decimal as a geometric series. Part B is what my elementary math students do, is they write it as a ratio of 2 integers. Now, it's possible that you know what this is. Does anybody know what this is? It doesn't have to be in a simplified form, but does anybody know what this is as a ratio of integers? So the answer is no. You're just guessing now, Dylan. What is it? So how did you get 4 11ths?
I guess.
You're guessing. Y'all are just guessing. Okay, so I can tell you what it is from the way it presents itself. It's 36 over 99. And then it's going to reduce itself. Okay? I know that because of the way the repeating happens. The repeating is over the 2 digits. Normally, if there were no repeating, this would be 36 over 100. Its pattern is going to make it over 99. I show my students in elementary math how to do it in a very different way. We're going to do it from a geometric series approach. This isn't reduced, obviously. We'd need to reduce it, and maybe it equals one of the things you guys have thrown out as possibilities. But we're going to see it, why it's working, first from the perspective of series, okay? So let's take a look at what we have here. If we're taking a look at 0.36 repeating, we're going to write it out in a few steps. So the first thing is, this is 36 over 100, except it's not because it repeats. But it is in the hundredths place, right? There's 2 digits. It's ending in the hundredths place. So this is, again, there's another 36 over the next one. So like if I were to write this out, let me write out a few of them actually instead. Like that. Let's go with that. So these 2 numbers are in the hundredths place. That's 36 over 100. These 2 numbers are in what place? What place value am I at? I'm writing a little bit too small. Let me make this a little bit bigger. What place value am I at in those second 36, 3 and the 6? 10,000, so that's right. So if you count over, we have 10,000 there. The next one, what place value are we in? It's the millionths. And each denominator is going to do this, increasing by 2 zeros as we go. Does that make sense for everyone? So we're writing this as an expansion in fraction form. What part of this remains the same? The numerator, right? It's 36. Every numerator is 36. All the numerators are 36. But the denominators are changing, right? They're changing by 2 zeros. Okay? So is there a way that I could write this denominator in this form, 100 something? Generally, yes. This one would be 100 squared, right? 100 squared would give me 10,000, agreed? How about this one? What is this one? 100 cubed, right? And the next would be 100 to the fourth. So Adam's exactly right. This is 100 to the k power. Okay, the first one's 100 to the 1, by the way. So I've written them in a condensed form that allows me to write the summation now in front. I need to figure out where k is starting. It's going indefinitely, so it's infinity. Where does k start for this expression? Yep, it starts at 1. Now, that's not exactly the way my geometric series is described to start. I mentioned this at the beginning, right? What is this supposed to start at for the geometric series to be able to say like a over 1 minus r? It's supposed to start at 0. Agreed? All right, so what would I get? So when k is equal to 1, a sub 1 is 36 over 100. That's our first term, correct? So we're going to adjust this, and we're going to adjust this as follows. My first value, which is a sub 1, is in fact 36 over 100. We know that. It's the first thing I wrote down. What is the ratio that gets multiplied every time? What am I multiplying by? 1 over 100, right? Every time it's 1 over 100 that I'm multiplying by, right? The powers of 100 are happening, okay? And this 100 is then increasing. It's the power k. I'm multiplying by 1 over 100 every time. And this will reset it back to the beginning, k equals 0 to infinity. So I just use the first value, that is the value when k equals 1, and it resets it back to k equals 0, okay? But I have to stop and actually ask myself, what is the first value? What is it increasing by? The other thing you can do is you can look at it even straight from here and jump there. That would be okay. 36 over 100 puts you right here. And then you can ask yourself, what am I multiplying by every time? I'm multiplying by 1 over 100. And that will lead you to this spot as well. Okay. Does it converge? Okay. It converges more than that. So ignoring where we started, the 0.36 repeating part, ignore that for the moment. Just looking at the series at the end. What kind of series do we have? Geometric. When does a geometric series converge? For what? A fraction for what?
R.
For r. When r is a fraction. Is r a fraction here? Yes, it is. What's the fraction that r is, or what value does r have? R is 1 over 100, okay? So R here is 1 over 100. Will this converge? Yes. Why? Because that's between 0 and 1. Exactly. So this will converge because 0 is less than 1 over 100 is less than 1. That's why it's converging. And because it's converging, so this is everything we've done to here. This is part A. Because it's converging, I can do part B. I can find a ratio of two integers. I can use that formula that we found for, or that we were given for the series summation for geometric series, like this. What's A? 36 over 100. What is R? 1 over 100. And we're going to multiply by 100 to get rid of that little fraction. Make sure when you do that, you distribute the 100 to the 1 at the beginning. So this gives me 36 on top, and it gives me 100 minus 1 on bottom. What's 100 minus 1? That's the 99 that I predicted at the beginning from the way that it presented itself, right? So what is 36 over 99? Well, we would reduce then. Do I have it written down? So it is 4/11ths. If that's the one you were guessing, is that right? Who was guessing that one? 4/11ths. Dylan or Preston? Somebody guessed 4/11ths. Preston did? Okay. So we end up with 4/11ths for that. How could we confirm that that's right? I mean, really, really. Your calculator. You could just take 4 divided by 11 and it will show itself as 0.363636 in the calculator, right? Yeah. Okay. So this is the process by which we can actually find a repeating decimal in geometric form. All right. Some properties of an infinite series. These are properties that we would expect to hold true, and they do. If we have a summation of a sub n and a summation of b sub n, and they're convergent series, a, b, and c are in the real number system. If the summation of a sub n is a, and if the summation of b sub n is b, then the summation from n equal 1 to infinity of c times a sub n essentially says I can just pull the c to the beginning. I'll have what's left over is the summation of the a sub n, and that's a. So it's c times a. Okay? So a coefficient can simply be shifted out, kind of like with integration, like with derivatives, like with limits when we were doing limits just of real numbers or real functions, all that, same thing. And the same thing's true for number 2, is that the summation of the two series, or the sequences, a sub n and b sub n, is the same as the summation of the series. So we have a and b sub n. So in other words, this can be separated into summation of a sub n plus the summation of b sub n, right? And those are a and b. So everything that we would want to be true and expect to be true is. So let's take an example of one then. This has a summation, in this case it's a subtraction or a difference, of two series. But I can actually separate it and think about each of the series individually. I don't have to think about them combined. This is 1 over 2 to the k minus the series from k equals 0 to infinity of 1 over 3 to the k. You don't have a lot of options yet. You have geometric and you have telescoping. Which one is it? It's geometric. It's geometric, okay? So these are geometric. The a value is what happens when we plug in 0 for k. So what is the a value? Let's just find the a value and the r value for each one of them. What's the a value for 1 over 2 to the k? It is 1. All right, if you put in 0, you get a denominator of 1, so you get 1. What is the ratio? It's 1/2. I multiply by 1/2 over and over and over again. Second one, what is the a value over here? It's 1 as well. What is my ratio? It's 1/3. We'll put the negative in front, but you could do it as you could do this as plus and then a minus here if you wish. I'm going to just do it as a positive, so 1/3. Either way, whether you do it as positive or negative, what can you tell me? Do these converge? Do they diverge? What do you know? They converge. How do you know? Yeah, those ratios are between 0 and 1, right? So these two pieces tell us that they both converge. And since they both converge, I can find their convergent values, right, their limiting values independently, and then I can subtract them. So I've got the a, I've got the r. This is a over 1 minus r. So a is 1 over 1 minus 1/2. And over here I have a is 1 over 1 minus 1/3. Ultimately, I'm going to subtract the two sequences summations together at the end. So your call on how you want to do it. I like to get rid of the little fractions, so I'm going to multiply by 2. So this is going to give me 2 over, do be sure you distribute, 2 over 2 minus 1. I'll do that in a second. And then I'm going to do the same thing over here, times 3. So this is going to be 3 over, again, distribute, 3 minus 1. So the first one's 2. What's the second one? 3 over 2, or 3/2. What happens when I subtract them? 2 minus 3/2. It's 1/2, or 0.5 if you prefer. It's 1/2. And obviously it converges. It converges, though, not because I got a 1/2. It converges because these up here already converged because they were geometric and they had ratios that were between 0 and 1. Right, so this point actually tells me it converges. This point actually, I'll take it from here, tells us what the limit is. All right, so this is S. S is 1/2. Okay, last thing for today. It's a real quickie. If your sequence converges, I didn't say that right again. If your series converges, there we go. If your series converges, it must be true that the limit of the sequence is 0. If your series converges, the limit of the sequence is 0. And that leads us to Theorem 9.9, which is actually our first test for divergence. If the limit is not 0, then it will not converge. It will diverge. And what you might remember from some logic you've done somewhere along the way is that's called a contrapositive. When you flip it around and you put negations on both pieces, that's a contrapositive. So if it converges, the sequence limit is 0. If the sequence limit is not 0, then it will not converge. It will diverge. You cannot use the divergence test to tell me something converges. The only thing the divergence test can do is tell if something diverges. We will have some tests that will tell us both things. Either way, it'll say it will or it won't. This test doesn't do that. It only tells us if it diverges. So if you take a look at this right here, if we were to look at the limit of the sequence 3k over k plus 4, do you remember as k goes to infinity, do you remember how we find that limit? We've done it recently, as in 9.1. It's 3. We multiply this by 1 over k, like this. This gives me the limit as k goes to infinity of 3 over 1 plus 4 over k. The 1 plus 4 over k part goes to 0. This limit is 3. So this limit is 3. What does that tell you about the series? It diverges. In other words, 3 is not 0. I know that's probably the most exciting thing you've heard today. 3 is not 0. Right? 3 is, I know, so 3 is not 0. So by the divergence test, the summation from k equal, we started with 1 on this one, 1 to infinity of 3k over k plus 4 diverges. Okay? If we had found that this limit was 0, what could we say?
Converges.
Nope.
It might.
It might. It might and it might not. If this limit is 0, if when we do this we get limit is 0, it means the divergence test is not the test we need to use. There's going to be some other test that's going to be able to help us. This is not going to be the one that's going to be useful. Okay? The divergence test cannot tell us anything about it converging. It only can guarantee if it diverges. We'll stop there for today.